learn how to sketch cubic function in terms of a bracket x minus h bracket to the power of 3 plus k. So first we're gonna focus on the transformation of the graph for a basic cubic function, which is x cubed. So the domain of this function will be x can take any all the real values. However, the range, which is the y values, is going to be different than what we have in the quadratic function. So in this case, x and y will have the same sign. So if x is positive, y will be positive. If x is negative, y will also be negative. And therefore, the range will be y is also all the real values. So here's some sketching about the cubic functions, and you will be able to see there is some dilation and reflection happen. So we'll go through it in later. So for the first basic cubic function, we can see the graph is an odd function easily. And just a bit recap about what odd function is when we have fx is equal to negative fx, negative f negative x. Okay, so what that means is now the negative x will be equal to negative. You replace x by negative x to the power of 3, and this will give you negative times negative x to the power of 3, and the answer is x cubed. So you're matching with the form of fx, therefore it is an odd function. So for an odd function, you will be able to see that there's no difference for the function to be reflected in the x-axis and in the y-axis. Okay? Then in this graph, there's a very key point in our sketching, which is right in the middle of the graph. Okay? So this graph is known as the stationary point of inflection, and the point is important because it has a gradient of 0 at this point. So if we sketch a tangent line of this point, you'll be able to see, if I sketch a tangent line here, you'll be able to see it becomes smaller and smaller for the gradient. And then at this point, the gradient will actually be becoming 0 at this point. And then it becomes larger and larger after the point on the graph as well. Okay, so it's concave down before the point and concave up after the point. So at this point, if you know the gradient is going to be 0 or having a horizontal tangent, we know this point is going to be a stationary point of inflection. And we will go through this when we go later in the topic of calculus as well. So this point has a gradient of 0. And then the second graph, which is y is equal to 3 times x to the power of 3, and we will be able to see there's a dilation by factor 3 in the x direction, and it has a similar shape towards the basic cubic function, but the graph now looks narrower. And again, there's an important point which also happening at the origin, which is 0, 0. And again, this point has a horizontal tangent and will give you 0 gradient. Okay, and the last graph, you will see there's a dilation by factor 1/2 in the x-axis, and there is also a reflection in the x-axis, or you can say it's in the y-axis because it's a function, so it doesn't really matter. And again, the important point of inflection was still happening at 0, 0. So at this point, you will still have a horizontal tangent. Therefore, if we have a dilation or reflection for a cubic function, it does not change the shape of our graph. You just become narrower or wider, but depend on the factor of dilation. So it's being reflected, you will see so you'll see the graph like this. If the dilation factor is a positive value, but if it's negative, then you will be able to see a graph like that. Okay, and that's something you're gonna be aware when you're sketching. So when you sketch a graph, don't sketch something like this, and you can't tell at this point it has a 0 gradient, because when you sketch a tangent line towards it, it is not horizontal. Okay, so please make sure that when you sketch your graph, do show a point which is going to be the one with 0 gradient. Okay, so be aware to show it's going to be a flat line at the point. All right, so now let's move on to the next slide. So we have stationary point form of the cubic functions, and it's very similar to the turning point form of quadratic equations, which is fx is equal to a bracket x minus h bracket squared plus k. And we know that this will give us the turning point at hk, and this will also tell you the transformation of the parabola from fx is equal to ax squared. So this, we're gonna focus on the translation of the graph. For some cubic functions, which can be also written in the stationary point form, I'll give you the coordinates of the stationary point. So not all the cubic functions will give you that, so only some of these. Okay? So the form is very similar to the turning point form of a quadratic functions, just the power here now becoming 3 instead of 2. So this will give you the coordinates of a stationary point of inflection at hk, and again this will tell you the transformation from the graph fx is equal to ax cubed. So we have a vertical translation if k value is greater than 0, which means we're gonna shift the graph in the positive y direction or moving the graph up. If the k value is less than 0, which means we're going to shift the graph in the negative direction of y, or we can say that it's being shifted down. There's also a translation in horizontal direction. If the h is greater than 0, the direction will be in positive x, and then if h is less than 0, it will be shifted in the negative x direction. So it's again exactly the same thing as what we did in the turning point form of quadratic equations. So now we will learn how to sketch a cubic function then. So if we'll be given the stationary form of a cubic function, which is this, we first need to identify the point of inflection. So in this case, that will be hk. Okay? And then the second thing, we want to find out the x-intercept by making the substitution of y is equal to 0 into the stationary form. Okay? And then we also make the y-intercept by substituting x is equal to 0 in towards this stationary point form again. And then we'll be able to start to sketch our cubic function. So now let's have a look for an example. Okay, so now the example asks you to sketch the graph of the function, which is y is equal to bracket x minus 2 bracket to the power 3 plus 4. Alright, so first thing is to find out the point of inflection. It's easy to tell, so it's going to be 2, 4 in this case. And to work out the point, the x-intercept, you substitute the value of y is equal to 0 into your function. So there will be x minus 2 to the power 3 plus 4 is equal to 0. So there will be x minus 2 cubed is equal to negative 4. So it is unlike taking square root on both sides. You can take a cubic root if you have negative value on the right. Because think about the case is if you have negative 2 to the power 3, that is equal to negative 8. Okay, so what that means is if you have cube root negative 8, this will give you the answer negative 2. So therefore, that is going to be x minus 2 is now equal to negative cube root 4, or you can say that's going to be cube root of negative 4. These two are the same. You can take the negative sign in front. And then what that implies is x is now equal to 2 minus cube root 4. And since cube root 4 is about the value 1.59, and then we can say 2 minus this is going to be equal to about 0.4. Okay, And then you can work out the y-intercept by making x is equal to 0. So y is going to be equal to 0 minus 2 to the power of 3 plus 4, which is going to give you negative 8 plus 4, and is negative 4. Okay, so now we have both the x-intercept and the y-intercept. So x-intercept will be 2 minus this, 0, and the y-intercept will be 0, negative 4. Okay, so now we can start our sketching. All right. Okay. So it's just a bit annoying. So first you want to identify where is the point of inflection. That will be at 2, 4. So it's going to be here. And then your x-intercept is at 0, that will be about 0.4. It's going to be somewhere around here. So for this point, the coordinates is going to be 2 minus cube root 4, 0. Okay, and then for the y-intercept, it's going to be negative 0, negative 4. So it's going to be here. And now we are pretty much able to sketch the graph by now. Okay, so all right, just try to sketch a graph precisely. And it looks like this. All right, so when you sketch, just be aware, like if I want to sketch it better. All right, okay, try to make the graph next to the point of inflection to be as flat as possible to show there's going to be a horizontal tangent. Okay, and that's gonna be the graph looks like. All right, now move to the next slide. So we now need to think about the inverse of our stationary form of our cubic function. So the first thing is, what's going to be the inverse of f(x) is equal to x to the power of 3? So this function is a one-to-one function, and we have seen that in the previous slide already. So think about the process for us to find out the inverse. So first thing, we're gonna let y is equal to x cubed, and now we're gonna swap x and y. So you will have x is equal to y cubed, and then you take cube root on both sides. You will have y is equal to cube root 3, or you can write that in other way around. Okay, so therefore the inverse is going to be cube root x, or you can write this into the index form, which is x to the power of 1/3. Okay, and then you will see their domain and the range also swap with each other for the cubic function and its inverse. And then you could find the point of the vertical tangent of this function if we know we are given the form f(x) is equal to a to the power of x minus h bracket to the power of 1/3 plus k. And the point again will be found at hk. And the reason why for that is we're gonna see this example. Okay, so we know we can find the inverse by reflecting the function according to the linear line, which is y is equal to x. So you'll be able to see the cubic function and also the function with the power of 1/3 sketching on the same axis. And then you will be able to see that for the blue one, okay, which is going to be x to the power of 1/3, at 0, 0 at this point, it has a vertical tangent, since the horizontal tangent at the point of the cubic function is also reflected according to the line y is equal to x. So now it turns into a vertical tangent. And therefore, you can find this point if been given the form of this. Alright? Again, just be aware when you sketch the middle point and this point, you have a vertical tangent. So in this case, for this function, the point is going to be 0, 0. Alright, so now how can we sketch a cube root function? It's very similar to the case for us to sketch a cube function. So we'll be given a stationary form of a cube function, which is this. Then you need to identify the point of inflection. Again, that is going to be hk. You find your x-intercept, and then you find your y-intercept. And now we will start to do the graphing. So here is the example for us how to sketch this function. So the point with vertical tangent in this case again will be pretty straightforward. That's going to be 1, -2. Okay, because the value of this. And then to find out the x-intercept, you make y is equal to 0. And therefore, x minus 1 to the power of 1/3 minus 2 is equal to 0. X minus 1 to the power of 1/3 is equal to 2. And then you cube on both sides. So you're getting x minus 1 is equal to 8. And then x is equal to 9. So the x-intercept in this case will be 9, 0. And to work out the y-intercept, you make x is equal to 0. So there will be y is equal to 0 minus 1 to the power of 1/3 minus 2. And it's going to be -1 to the power of 1/3 minus 2. And that's going again to be equal to -1 minus 2. And the answer is -3. And therefore, the coordinates of your y-intercept is going to be 0, -3 in this case. And now we need to start to sketch our graph. Okay, so that will looks like this. The point of inflection, they'll be at 1, -2, so it'll be here. All right, go back to that slide. And then your x-intercept will be at 9, 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So it'll be here. And then you've got your y-intercept at 0, -3. So it'll be here. All right. And then you will be able to sketch the graph. And do it slowly. All right. The graph will look a little bit weird. Just make sure at that point it looks vertical to you for the tangent. Okay. All right. Okay, so that's gonna be the graph of this function. So I will label the points as well. So here is going to be 0, 9, 9, 0, sorry, and here's going to be 0, -3. And for this point, the coordinates is going to be 1, -2. And we are done. All right. So then we want to find out the inverse function for this cubic function. Again, we will let y is equal to 2 times x minus 4 to the power of 3 plus 3. And then we're gonna swap the position of x and y. So you have x is equal to 2 bracket y minus 4 cubed plus 3. And then you rearrange it to have 2y minus 4 to the power of 3 is equal to x minus 3. And then divide by 2 on both sides, you will have this. Then you cube root on both sides, you have y minus 4 is equal to cube root x minus 3 to the power of 2, over 2. And then y is equal to 4 plus cube root x minus 3 over 2. Okay? And again, you will be able to see for this inverse function, the domain and the range, both of them are going to be all the real numbers. Since for the cubic function, the domain and the range are all real numbers, so even you swap that, and it should still be all the real numbers for x and y's in our inverse. Okay, so that's the thing about this exercise. Here is the exit ticket question for this exercise. Now you can pause the video and have a go for yourself. And we will go through the answer in a minute, so you can check your understanding of this concept. Okay, so now in the question, we want to find out the inverse function of this fx and then sketch the inverse on our Cartesian plane. Okay, so our first goal is again to let y is equal to x plus 1 to the power of 1/3 minus 2, and then swap the position of x and y. Then you will be obtain x is equal to y plus 1 to the power of 1/3 minus 2, and again rearrange it, so it will be x plus 2 is equal to y plus 1 to the power of 1/3. Then you cube on both sides, and you will obtain y plus 1 is equal to x plus 2 to the power of 3. And then y is equal to x plus 2 to the power of 3 minus 1. And this is actually the stationary point form of a cubic function, and we've done that already. And then you can find out the stationary point of inflection, which is going to be -2, -1. And then the x-intercept, you can find it by making y is equal to 0. So let's do the calculation up here. It's going to be x plus 1 to half, it's going to be x plus 2 to the power of 3 minus 1 is equal to 0. So x plus 2 to the power of 3 is equal to 1. X plus 2 is equal to is equal to 1. If you take the cube root on both sides, and then which tells you x is equal to -1. Okay, and then you also need to find out your y-intercept by making x is equal to 0. So that will be 0 plus 1 to the power of, that will be 0 plus 2 to the power of 3 minus 1. Therefore, it's going to be 8 minus 1, and the answer is 7. So the y-intercept will therefore be 0, 7. And now you'll be able to sketch the graph. Okay. So it will be here. The stationary point will be -2, -1, so it will be in the third quadrant. Here. -1. Okay, this point will be -1, -2, -1, and the x-intercept will be at -1, 0 here. And the y-intercept will be 0, 7. 1, 2, 3, 4, 5, 6, 7. So it'll be up on here. Alright, and then you'll be able to sketch the graph. And do make sure, because this is a cubic function, you need to show a horizontal tangent at the stationary point. Okay, so let's do it. And the graph should look like this. Alright, or you can make it look even more flat at that point, and this will be the graph for this cubic function. Okay, so here's everything for this exercise, and the next exercise will also be done as a podcast, so please find it yourself and listen it during your holiday.